Hi all, we're Team Ask and we will be presenting on machine-generated actions for sound event classification. Sound event classification is the task of identifying active events in audio. We want to automatically identify actions for audio, which can be beneficial to sound event classification tasks. This is significant because automatically generating action information will eliminate the need for expensive human annotation. Traditional machine learning approaches for sound event classification use MFCCs, log-mel spectrograms, and audio embeddings. Recently, Elizalde et al. Showed that explicitly including crowdsourced ratings about actions producing an event can help generalization ability of machine learning models for sound event classification. Actions here represent the physical properties of sound, such as rotating and dripping, whereas sound events are the actual events described by a sound, such as birds chirping or raining. We use deep learning models to automatically generate action vectors as seen on the right. We compare our generated action vectors with human annotated ones by measuring improvements in sound event classification task. We use the ESC50 dataset for training and testing both action vector generation and sound event classification. We use the results on sound event classification as our baseline. State-of-the-art OpenL3 audio embeddings concatenated with crowdsourced action vectors resulted in an 8% increase in accuracy when compared to just using audio embeddings. We use two approaches for generating action vectors. In the first approach, audio embeddings are used to train a multi-layer perceptron to produce normalized scores for each action class. And in the second approach, we fine-tune a pre-trained audio neural network, or PAN, to produce action scores. The action vectors generated by these models are used to train a MLP to evaluate their performance on sound event classification. We use the same architecture and hyperparameters as Elizalde et al. To isolate the effect of using different input representations. We run each experiment 5 times and report the mean. And here from the table, we observe that concatenating audio embeddings with the generated action vectors actually results in an increase in sound event classification performance, suggesting that our generated action vectors actually may carry additional useful information. While comparing the performance of the action vectors generated by the MLP versus the PAN, we found that the PAN-generated action vectors performed better in isolation and in conjunction with the audio embeddings. Interestingly, both outperformed the accuracy obtained by using log-mel spectrograms as reported by Elizalde et al. To compare our MLP-generated action vector versus the PAN ones, we look at the heat map. Actions here are along the x-axis, and the sound events are along the y-axis. The leftmost heat map corresponds to the true action vectors, and we hope to produce action vectors that are most similar to that. Taking a closer look at the heat map for generated action vectors, we observe some interesting differences. In the highlighted box are the action scores for the action class breaking, and we see that PANs are able to capture the information that MLPs completely miss out. And overall, PANs produce higher scores for action classes. For generating action vectors, we minimize the squared error. We also computed the classification accuracy while predicting the top action as a proxy metric. Interestingly, we found that although the MLP achieved a lower MSE and a higher action classification accuracy, but in sound event classification, it actually performed worse. Also, in the heat maps, we saw that infrequently annotated actions such as sizzling were not being captured adequately. So we chose the top 10 actions based on frequency, which resulted in 88% of the audio having at least one action. We used those actions for generating action vectors and sound event classification. And we found that these 10-dimensional generated vectors preserved most of the useful information that their counterparts in 20 dimensions had. So now let us look at an example. In this clip, we see that when a MLP is just provided with the audio embedding, it classifies the sound incorrectly as rain. So the sound is actually of a helicopter, and when the network was provided with action information, it actually correctly classified it as a helicopter. And we can sort of intuitively see that by looking at the action vector, which is high for actions like rotating and blowing and vibrating. So to conclude, our work suggests that generating action vectors is a useful idea, and this idea drives our future work, in which we want to test our generated action vectors model on other sound event datasets to further explore the efficacy of generating these features. Thank you. Why do you stop in the middle?